Today we're going to be talking about z-scores, probability, and area under the curve. So I'll explain what all those mean as we get through this lecture. These are all really important concepts for when we do inferential statistics and inferential testing. They'll also be quite useful for psychometrics. So let's get into the details. So last week we talked about a mean and a standard deviation, and the mean and the standard deviation together gave us some idea of what the curves look like, kind of the spread of the curve and where the middle is. So if we look at these two curves in this slide, we've got mean at 70 in both of them. We also have different standard deviations. So in this first distribution, again, the mean is 70, and we have a standard deviation of 3. So a score of 73 is one standard deviation away. In this distribution, the standard deviation is 12. So if we have a score of 76, it's much further away in this one on the left because it's 2 standard deviations away. In this distribution, it's a half a standard deviation away. So it's very different distributions. And so when we're asking the question, what does the score of 76 mean? We need both the mean and the standard deviation. So again, just to kind of highlight this again, in this distribution, if somebody received a score of 76, they're doing outstanding, way better than most everybody else in this distribution. So their score is here better than 98% of the people. If the score of 76 is in this distribution, they're still doing better than the majority of people. They're still above the mean, but it's less people below them, I guess you might say. So they're half a standard deviation above the mean versus 2 standard deviations above the mean. So what we want to do is have a way of describing these scores and something that can kind of quickly tell us how much better or how much worse somebody is than the average. And the z-score is a way for us to do that. So a z-score is a standardized distribution, and let me just actually show it. This is the z-score distribution where the mean is at 0, and then 1 standard deviation is a score of 1 on the z-score, and then 2 standard deviations is a score of 2. So it just puts everything on this standardized metric where the mean is at 0, and then you see the standard deviations as the z-score. So we can transform, something like an IQ test has a distribution where the mean is 100 and the standard deviation is 15. So 1 standard deviation above the average is 115, 2 standard deviations above the average is 130. So that would just correspond to a z-score of 2 instead of a score of 130. So we can convert these z-scores pretty easily if we want to. So again, here's a different distribution being converted to z-score. So in the distribution on the left, we've got a mean of 100, a standard deviation of 10, and we convert it to z-scores. Now we have a mean of 0 and a standard deviation of 1. All right. So with the z-score, this is just a little bit of a primer to just make sure that you're getting this. Of the following z-scores, which one represents the location closest to the mean? And the correct answer is A. So I'll just kind of go back a slide to kind of show you where these others are. So we've got 0.5 is the one we just had here. We had +1, -1. I forgot if it was -2 or +2, but either way, those are all further away from the mean. So we want the absolute value, the number that's the closest. It doesn't matter if it's negative or positive. All right, so here's a little formula just how to convert z-score or convert scores into z-scores. So we've got these 2 students, Maria and Joe, and Maria got a score of 64. Joe got a score of 43. We can say that Joe got a lower score than Maria, but we don't really know how that is on the standardized distribution. So if we have our original distribution with a mean of 57 and standard deviation of 14, what we can do is just use this formula to calculate where each person's score is. So Maria is at 64. She is a half of standard deviation above the mean. Joe is at 43, so he'll be 1 standard deviation below the mean. And then here's the score. So above we have the original distribution with 57 was the average, and the 14 is the standard deviation. So, and below is our Z distribution. So we see Maria's score here up on top is 0.5. Her score is 64. So she's right here. And then Joe's score of 43, he's 1 below the standard deviation. All right, here's a few questions to just kind of test your knowledge. Population with a mean of 80, standard deviation of 10. What is the Z-score corresponding to X equals 85? So if somebody gets a score of 85, what's their Z-score? We can use that formula and plug it into the formula. The way that I also think about, I just think about it doing it quickly. We know this is above the mean, so it's going to be a positive number, and it's 5 above the mean, and the standard deviation is 10, so it's a half of a standard deviation. So the answer is going to be 0.5. All right, so if we got a population with a mean of 80, standard deviation of 10, same as the last time, what's a score of 70? We know it's below the mean, so it's going to be a negative number, and standard deviation is 10, so it's 10 below the mean, so it's going to be 1 standard deviation below the mean, so the Z-score of -1. This one, population with a mean of 60, standard deviation of 8. What is the value corresponding to a Z-score of -0.5? So now we've got the Z-score, and we want to figure out what the person's actual score is. So we know that the mean is 60. This person is below the mean, a half of standard deviation. So half of 8 is 4. So they're 4 below 60, or 56. All right, same standard deviation or mean and standard deviation. Now a score of Z equals 1.5. So we know that the standard deviation is 8. So I'm going to be 8 above the mean plus another half of standard deviation, another 4, so 12 above the mean. So that gives me an answer of 72. And I'm doing this kind of quickly in my head. If the formulas, probably the best way to do it and do it by hand with the formulas, but I just want to do it in my head quickly so you have the answer and you can work it out with the formula on your own. All right, so population of scores has a mean of 44. An X value of 40 corresponds to Z equals -0.5. So we know that that's a half a standard deviation below the 44. So I know that the 8 must be the actual standard deviation. All right. So population with a standard deviation of 10, a score is located 20 points above the mean, would have a score of 2. So it's 2 standard deviations above the mean. We don't need to even know what the mean is because we're putting it on the Z-score. And so the Z-score, we know the mean is 0. So we know it's 2 standard deviations above that mean. All right, and then this one's kind of a simple question. Mean for any distribution corresponds to a Z-score of 0. So the mean is always at 0 on the Z-score. All right, so when we look at, a study here, we've got, this is what we're going to eventually get into with t-test. We're looking at 2 groups, and we're trying to see, are these groups different than each other or the population? So if we've got a score for one group is 418, we see that it's almost standard deviation above the mean, and then 450 is 2 standard deviations above the mean. So we would think, and we'll get into this probability piece in a minute, but we would think this is no longer part of our population just because it's so extreme. And if we look at the area under this curve, there's not many people in this area. So when we're starting to get into inferential statistics, we're going to try to figure out what is the probability that this score came from this distribution. And when it's far out there, the probability that it came from that distribution becomes much smaller. So this is a formula that you don't have to know or remember, but this gets at that area under the curve. And this is really important when you're doing testing and psychometrics, because you can figure out what percentage is a score better than the average, or how many people scored below this score. This is the full formula, but I'm going to give you a simple way to figure this out. And the simple way that I remember it is that for each of these different areas, put a little highlighter here, so 34% of the people are in this area, 34.13 to be a little bit more exact. So 34% of the people are here, 14% of the people are here, and then 2% of the people are here. So if we just have those simple numbers, forget the decimal points, I just remember 34, 14, and 2. If we add that up, that equals 50. So 50% of the people are above the mean, and then we could do the same thing and add it up. This is again 34, 14, and 2. 50% of the people are below the mean. So we can figure out where a score is, what percentage of people scored below that score or above that score with these 3 simple numbers. So I'm going to go into some questions, and this one I just answered. What percentage of people scored better than the mean? So 50%. I add 34, 14, and 2 up together, and I get 50%. So 50% scored above the mean. All right. So vertical line is drawn through a normal distribution at z equals -1. The line separates the distribution into 2 sections. The larger section corresponds to what percentage of the distribution? So it's at -1, and they're trying to figure out what is the area, how many people scored better than -1. So we know that 50% scored better than the mean, and then we know that this area is 4. So again, 50% scored above the mean, and then another 34% scored in this area here. So that gives us a total of 84% of people scored above the mean. So this is answer is B. Okay, so a vertical line is drawn through a normal distribution at z equals -0.5. So I'm going to put this right here, and proportion of the distribution that is located between the mean and the line is, so that's this area here between the mean and that line. And we've got a few different answers. So one, I'll tell you, it's never negative because it's a proportion, so that's always a positive number, so I can rule out A and C. And what I'm trying to figure out is how much is here. And we know 34% exist in here completely. So what I have to figure out is what is this portion here. And we've got, if I split it in half, 34 and half is 17%. And so 19 is closest to 17%. We've got a little bit more in this little top section here because the curve gets a little bigger, so that's why it's more than 17. So the correct answer is B. All right, and in this one we've got a vertical line drawn through the distribution at -0.5. And what percentage between the, that's the exact same question. All right, so here we have a bunch of distributions. We can kind of figure out how many people are above the line here. So we've got 14 plus 2, 16%. How many people here, we can calculate that, and how many people here. So with all of these, we can start to calculate those things by our numbers. All right, so here's a question for you. What percentage of people have an IQ score below 130? So this is 2 standard deviations above the mean. And so we know 50%, my coloring's not working on this red, but 50% is below the mean. We've got another 34% at 1 standard deviation, another 14% at 2 standard deviations. So 50 plus 34 is 84, plus another 14 gives us 98. So 98% of people score below 130. And then here's another one. What proportion is proportion in the tail beyond 1.5? So that answer is 0.0668. What's portion of people are z-scores less than 0.86? And so we know that if it went all the way to 1, it'd be 84%, and it's at 0.86, so the correct answer is C. All right, there's a lot of these questions. What's normal distribution, the z-score, the value that separates the lowest 80% from the lowest 20% from the highest 80%? So we got to find where 20% of people are here, and it's probably going to be right around minus 0.84. All right, I'm going to skip over a few of these. All right. So what we want to get to in this eventual probability under the curve is, again, we're going to be looking at what is likely not coming from this distribution. So if we have something that's coming from a far off place in this curve, either on one end or another end, then we think it might not be very probable coming from this distribution. So if, for example, that IQ score, if somebody has 140, could be somebody that's really, really smart, or it could be just a mistake maybe made in the reporting of the score or something. It doesn't seem very likely that that score could be 140. So again, we're trying to look at the likelihood of the score coming from the distribution, and when it's out in these far areas, it's very unlikely, where this middle part is very likely. So that's going to become our null hypothesis testing. So if you remember with the null hypothesis we always set up as there is nothing happening. There's so no relationship, no difference between the groups, no association, so nothing is happening. So we either reject or we keep that null hypothesis. And so what we're going to look for is a critical value. Is what's the probability that the null hypothesis is correct? And quite often you see that p less than 0.05, p is less than 0.05. That's the probability that the null hypothesis is correct. And if it's smaller than 5% or 0.05, it's not very likely. And that's when we reject the null hypothesis. So again, when we see the probability that p is really, really small, then we reject that null hypothesis. And just again, put it in a figure. So when our p-value, the probability, is really, really small, then we can reject the null hypothesis. If our value is in here someplace, it's quite likely that it came from that distribution, so we can keep that null hypothesis. And this is, we'll do things differently. We won't look things up in a table. We'll actually use the computer to tell us what the p-value is, but what we would used to do is look things up in a table to find the probability. If a score is here, what's the probability for that score? And that's how we would reject the null hypothesis or not. All right. So one other thing that I want to get into is this idea of the null hypothesis testing. We've talked a bit about this, and that knowing whether there is a significant difference or not is useful, but maybe what's more useful is how much of a difference. And we've talked about effect sizes and how much of a difference. And so Jacob Cohen is one of the people who really pushed this idea of effect sizes, and we should be looking at things like effect sizes. And he has what's been named after him as a D as a measure of effect size. So simply put, this is the mean difference between groups. If we're going to be doing a t-test, that's what we'd be looking at, divided by the standard deviation. So with Cohen's D, it's not affected by sample size, and we can look at the overall effect and how big it is. So for example, if we've got these two distributions here, we have a Cohen's D on the top of 0.15, so a small effect, and on the bottom we have a Cohen's D of 1.0, and that's a very large effect. So if we did an intervention to improve IQ scores in this example, this bottom intervention seems to have a very big effect, where the top intervention, it might have a significant effect, but in Cohen's D term, it's a small effect. So this is a small effect and a large effect. Both can be clinically significant, and that's going to really be dependent on sample size, and we'll talk about why it's dependent on sample size. Null hypothesis testing and clinical significance is dependent on sample size, so we'll talk about that later. But in this situation, the Cohen's D tells us a lot more than just whether it's significant or not. And then this is an example from a famous article, Rosnow and Rosenthal. They did these two interventions, and one found treatment A was more significant than treatment B. The other person who had come up with treatment B said, didn't find a difference between the two and said there's no difference. They're both equal. And when you look at the numbers, it really is dependent on sample size. And I'm going to get into this in much more detail when we go over the t-test of why that's the case. But this value in parentheses is related to sample size. So in this first study, there's 80 people. In the second, there's 20. And the reason they didn't find clinical or statistical significance is because of this sample is just much smaller. This one is a bit bigger. And so this one they found a significant difference, this one they didn't. But when we look at it, they have the exact same Cohen's D. The effect size is the same. It's the sample size that is the difference between the two studies. So we'll get into, again, more detail of that as we go through things, but I wanted to give you a little bit of the logic behind our inferential test, and what we're looking for is area under the curve being really, really small, so we reject that null hypothesis.